pi over 12. So that'd be 7 pi over 12. And once you get the pattern, you can just sort of keep going with it, right? 13 pi over 12. 19 pi over 12, that's a new one, right? So I just keep adding 6 pi over 12, right? So 1 plus 6 is 7, 7 plus 6 is 13, 13 plus 6 is 19. The next one would be 25 pi over 12, but that's coterminal with pi over 12. So I'm kind of done, huh? Oh, what about the negative ones? Yeah. So, but if I want them to be positive, I would say negative pi over 12 plus 6 pi over 12, well, that's 5 pi over 12. Then I think 11 pi over 12, and 17 pi over 12, and 23 pi over 12 is not quite, that's negative pi over 12, that's coterminal with negative. So if you just want the positive positions between 0 and 2 pi, there's 8 of those, 4 of those, and 8 of those, giving you 20 different positions.
Nice.
Yeah. On, you know, and then all their coterminal angles. All right. So, should we look to the book for more? What have I got here? Any questions from your homework in the, what are you stuck on these days?
Oh, you have a lot.
I got an email from Armando.
Yeah.
You're stuck on everything.
Pretty much. I'm on that same page.
Stuck on everything. So how about this? Does this make sense to you at this stage? Or? Oh, it's easy when I do it. That's right. That's yeah.
It's really easy to see and explain. Pretty much like when I get home and start looking at my homework, it's like written in Japanese or something.
So you just gotta, you know, remember what you know. And there's a lot of different ways of knowing these things. So it's good to know things in more than one way, right? So here I'm just saying, look, if I've got a polynomial, a function polynomial in a single trig function, then I can factor it, or then I hope I can factor. What if you can't factor it? Which can happen, right? There's lots of polynomials that just don't factor neatly or at all.
And that's where you would have to use like C in the highest power to.
Yeah, well, at that stage, you're calling on the higher authorities, and we just don't go there very often.
So we expect to see this on our.
So you should be able to factor it, right? If you get a cubic polynomial, there should be at least one rational zero, right? And here there were, 3, right? Cosine could be 0, that's a rational number. It could be 1, or it could be a half, right? So 3 nice rational zeros, and then that gives us 3 trig equations, right? And so the main tool with trigonometry is the unit circle. So if you're stuck in like, what's going on, start drawing unit circles and saying, well, where is cosine 0? Where is cosine 1? Where is cosine a half? And then once you got those angles, then you can say, well, any angle coterminal with those is also a solution. And that's where we get the so odd multiples of pi over 2 are all the places where cosine is 0. So if cosine 4x is 0, that means that 4x is an odd multiple of pi over 2. If you're at 1, that means you're over here at some angle coterminal with 0, which is some multiple of 2 pi. Could be just 0 times 2 pi or 0. That's a multiple of 2 pi, right? It could be 2 pi, or it could be 4 pi, or it could be negative 12 pi, right? Any multiple of 2 pi will do, any integer multiple. And then here, right, there's 2 positions for any value of x between -1 and 1, right? At 1, there's only one position. At -1, there's only one position. But anything in between, there's going to be 2, up and a down, right? So that gives us a plus or minus pi over 3, where the cosine of 4x is 1/2, or any angle coterminal of those. And then that's 4x, so to get x, you just divide through by 4. Remember, you divide both terms here by 4. And it gives you these. And you just start plugging in k equals 0, k equals 1, k equals 2, and you get all your values between 0 and 2 pi that way. Usually you can sort of suss out a pattern as you start doing that, right? And here you can see the patterns. Keep adding 6 pi over 12. That gives you all those. Yeah.
I just have a quick, like, clarifying question. So generally you add 2k pi. How come with tangent you just add k pi?
Because sine and cosine have a period of 2 pi.
Right.
Tangent has a period of pi.
Is that in a different terms?
Yeah, so when you graph the tangent function, it's got a vertical asymptote of negative pi over 2, right?
Right.
And another one at pi over 2.
Correct.
And so, looks like this, and that's one complete waveform for tangent.
Yes.
So that's an interval of length pi.
Got it.
So you're going to repeat that over here. And now 3 pi over 2 is the next vertical asymptote. And then at pi here, that's 0, and then here's that waveform.
Right.
Right, so if you've got, a number here, like say x, and that's the solution, then just go pi down the road, and you got, x plus pi is also a solution.
Whereas cosine and tangent are double that.
Yeah, right. And so part of the deal there is if you look at the unit circle, and you see, here's a point x, y. The ratio of y to x is the same over here as it is there, right?
Okay.
So this is negative x, negative y. It's got the same ratio.
Right.
Yeah.
Right. So for tangent and cosine it's different, or for sine and cosine it's different, but tangent it's analogous.
Right, so cosine is x, right?
Yeah.
And so that's going to be, you got to go all the way around to get.
Is there any other condition in which you would have put the 2 in front of the I, k? I just.
Well, I guess cotangent is also,
That those are the only conditions?
yeah,
Okay.
cotangent and tangent, which raises a problem. So we have this identity, which appears on page 550. Can we go to page 550 in the book? This is 550. Yeah. Well, yeah, that is it. So in fact, 549, huh? Is that 549 or 550? 549. So let's look at page 549, where there's sort of an important identity. Which I don't know if we discussed in fullness yet. And it kind of relates to your question about tangent in an interesting way. So let's see, so page 549, we find this identity, that if you have A times, how do they write it? A sine x plus B cosine x. That's always equal to k times sine of x plus phi for some k and some phi. So k and phi will be determined by a and b. So there's these parameters. So x is a variable, right? And this is an identity that is true for all x. But for any particular a and b, we can produce a k and a phi so that this will always be true. And so here's the formula for k. K is the hypotenuse of a right triangle with legs a and b. All right, so you can sort of envision that like so, right? So which one is which? I guess, yeah. yeah, in fact, I think this is gonna be B, and this is gonna be A, and this is gonna be phi. But this is on the unit circle, so yeah, thinking about it as a right triangle works in the first quadrant, but beyond that, you have to be a little bit more careful, right? So, so what about phi? What is phi? Well, phi is determined by y and x, right? Or it's, I guess, A and B. Maybe should we write A and B? So if we're here, that means A is here and B is here, right? And so this is the angle whose tangent is B over A. Right? The opposite side has length B, the adjacent side has length A, right? The right triangle there. And the hypotenuse is length 1, right?